Alright, so we now start a new section, the axiom of choice. This is the final axiom in our Zermelo-Fraenkel choice set theory. So before we discuss this axiom, let us go through the axioms that we have seen so far briefly. So these are the axioms that we have seen, which tell us, collectively they tell us what sets are and how they behave. So the first axiom was this: sets are objects. What it means is that sets can be elements of other sets. Then the second axiom was the axiom of empty set. It postulates that there is a set having no element at all, and we call that set the empty set. Then the third axiom is the axiom of singleton sets and pair sets. That is, this one tells us that given any object, there exists a set having only that object as its element. And if we are given two objects, not necessarily distinct, then also there is a set having those objects as its only elements. So that is the axiom of singleton sets and pair sets. Then the axiom of pairwise union, which tells us that if we are given two sets A and B, then their union exists and is also a set. Then we have the fifth one, the axiom of specification. What it says is that if we are given a set A and some property P of x pertaining to the elements x in A, in the sense that for a given element x in A, the property is either true or false, then the collection of all those elements in A for which the property is true is a set. Okay, that is the axiom of specification. This is a set. Then we have the axiom of replacement. Now this one says that if we are given a set A and for any element x in A and any object y, if there is a property P depending on x and y such that for each x in A, there is at most one object y for which this property is true. Say that is the restriction on this property. That is, for each x in A, there is at most one y for which this property is true, then the set of those objects y such that the property is true for some x in A is a legitimate set. That is, that collection is a set. That's what the sixth axiom tells us. It's called the axiom of replacement because here we are replacing each element x of A by something, by that y actually, for at least one, that is, they mean the same thing. And you see here we have at most one y, right? So for some specific x in A, maybe there is no object. So then we do not have anything for that corresponding x. For those x for which we have one object, and in that case it will be precisely one object, we replace that x with that y. So that means actually we are replacing some elements of A by some corresponding objects y, and that collection of those replacements is a set. That is the sixth axiom. The seventh axiom is the axiom of infinity. This one introduces an example of an infinite set in our set theory. So basically what it says is that there exists a system of natural numbers. That is, there exists a set consisting of an object 0, and there is an increment operation such that for every n in n, there exists its successor in n that satisfies those 5 piano axioms. Okay, such a thing exists, and the existence of that itself is this axiom of infinity. Then the eighth one we came across is the axiom of universal specification. Which I'm not again going to say what it was or what it is. Let's just recall that it gave rise to Russell's paradox, which is why we discarded this axiom, and to rectify the situation we introduce another axiom. So that means this is not a part of ZFC. This is the axiom of regularity. What this one states is that if A is a set that is non-empty, then there exists at least one element x in A such that either this element x itself is not a set, or when it is a set, then it is disjoint with A. And this axiom of regularity allowed us to get rid of Russell's paradox. With this axiom, there is no Russell's paradox. We have already seen these things, such that either x is not a set, that means x is a primitive object, or x is a set and it is disjoint with A. The intersection of x and A is empty. So that is the ninth one. Then the 10th one is the axiom of power set. So what this one says is that if we have two sets x and y, then the collection of all the functions with x as domain and y as range is also a set. And that set, we have a symbol for denoting that set is this. So this axiom says that that collection is a set. If we consider the collection of all functions from x into y, that is a set. Then there is another one, the axiom of union, which says that if there exists some set I, well, actually that's not how this axiom is given originally. Originally the axiom is given like this. Suppose you have a collection of some sets. Okay, that means a collection which itself is also a set and all the elements in it are also sets. That is, a set of sets is given to you like this. It has some sets A, B, etc. Who knows what the sets are, but some sets are given and all the elements in this collection are sets, and also it is given that the collection itself is a set. Not every collection of objects is a set, we already know that, we have seen such examples. Then there exists a set that is the union of all the, well, I have in fact made a mistake here in this notation. Rather, I should have said this. Let me just write it, okay, for once. Let A be a set whose elements themselves are sets. Then there exists a set which we denote by this symbol, whose or consisting of all the elements of the elements of A. What that means is that the elements in A are themselves sets. So we are considering the elements of those sets, taking them together, and with them we are forming a new set. That set is this set of the elements of A. So that is the axiom of union. And these are the axioms we have seen so far, and whatever we have developed so far have arisen from these axioms only. So they form a bedrock of what we have done so far. But now we are going to introduce our last axiom, that is the axiom of choice. And here the author has some things to say. So what he says is that we have delayed introducing this last axiom for a while now, just to demonstrate the fact that a large portion of analysis can be constructed, can be developed without that axiom of choice. But there are some situations where we do need axiom of choice. And besides, when you use axiom of choice, things become very simple in some situations. But the problem with the axiom of choice is that when we will see that axiom, when we see its statement finally, when we understand it, it will be very plausible, just like the other axioms. See, the axioms form the bedrock of our system because each one of them is so easy to believe that we do not need any further justification. We do not need to prove them by using something else, something more fundamental. We have decided to consider these things as our starting point and then develop our theory from that level, right? So just like these other axioms, the axiom of choice is very easy to see, that you will feel, the moment you see it, you will feel that yes, it should be true. But there is a problem. The problem is that although the statement is very plausible, but there are some consequences of this statement that are not very plausible in themselves. So that makes some people think, some mathematicians think, that there is something wrong with the axiom of choice. But that was the case when the axiom was first introduced. At that time, people thought that no, we are not going to agree with this axiom. We don't accept it because it gives rise to some very unintuitive things which we feel that they should not be true. So that means there is something wrong with that axiom. That's what people felt. But nowadays, most mathematicians accept this axiom. And the author says that there is another reason for this confidence in the axiom of choice. It's because there is a result proved by the logician Kurt Gödel, who gave that incompleteness theorem. Okay, what he proved is that any result proven using the axiom of choice will not contradict any result that is proved without the axiom of choice. So that means in our logical system, which so far has 11 axioms, it's like somewhat like this. Now, this is your system where you have 11 axioms. This is the starting point of your universe, and all the statements that you can form that can either be proved or disproved using these axioms alone form the logical universe of those axioms. That is, each point in this universe is a statement that can either be proved or disproved using these axioms, not directly maybe, but using other results that themselves are proved from this starting point. So that if one goes back, say you have some statement here, why is it true? Because of some other statement. Why is that true? Because of maybe some other statements. Like that, if you continue your backward journey, you will eventually reach this bedrock of your most fundamental axioms. However, what Gödel proved is that you can in fact neither prove nor disprove the axiom of choice from these axioms. That is, this axiom of choice itself, this statement lies outside this universe. So if you introduce this axiom, that means it is something coming from outside, and there is no harm in doing that, because introduction of this axiom and thus creating a new system does not give rise to any contradictions. It does not give rise to an inconsistent system where you are able to prove that something is true and simultaneously false. That does not happen. So because of that, the axiom of choice is generally accepted. Okay, now let us see what the axiom is. Now the axiom is given in the using Cartesian products. If we can in fact understand the basic idea without using Cartesian products also, but we have to formulate things rigorously, right? I need some ink before that. So that's why we are now going to go back to Cartesian products, but the notion of Cartesian products we have seen so far is somewhat restricted, and we need more. So we have to now define the most general notion of Cartesian products, where the number of sets involved is no longer necessarily finite. It can be any number. So let's now see what those things are. Now, before we see the actual definition, let's just go back to the idea of Cartesian products itself. We know actually what Cartesian products are, but still, say we are given two sets, A and B. What do we mean by their Cartesian product? The definition is extremely simple. The Cartesian product of A and B in that order is the set of all ordered pairs A, B, where A is coming from A and B is coming from B. All such ordered pairs are collected together, and that gives us the set which we are calling the Cartesian product of A and B, A times B. But that requires us to know the notion of ordered pairs itself, and that notion is also very straightforward and simple to understand. An ordered pair can be thought of as a set of two objects, but it's an ordered set of two objects. Unlike an ordinary set where order does not matter, here order matters. And this idea itself can be made more rigorous using functions. So what you do, instead of just simply postulating that such an object ordered pair exists, you can also do this thing like this. Say you think of a function f from this set 0, 1 into the union of A and B. That is the union of the two sets given, whose Cartesian product we are defining. Okay, now there can be many different types of functions possible that are of this type. Let us take one example, a concrete example. Suppose A consists of A and B, and B consists of C and D, right? Then the Cartesian product of A and B is actually, it's going to be what? A, D, B, C, and B, D. Now the functions that we were talking about here, in this case, you can see all these things in terms of functions like this. Say you think of a function this, which is defined by this rule. F of 0 is A and f of 1 is C. Okay, then this function corresponds to this ordered pair, and one may define the ordered pair itself to actually be this function itself. Why is that so? That's because we can interpret f of 0 as the first coordinate of the ordered pair and f of 1 as the second coordinate. It would be nice if we take 1 and 2 here, but because we are starting from 0, so we are maintaining that. Okay, so this function corresponds to this ordered pair. Let me just call it f1. Then we can clearly imagine another function corresponding to this ordered pair of the same type f2, such that f2 of this is f1, this is f1. f2 of 0 is a and f2 of 1 is d. But the four functions that you will get like this from this situation are not the only functions from 0, 1 to a union b. There are other functions also possible. For example, you can think of a function, let me call it say g. And say g of 0 is c and g of 1 is d. It is also a legitimate function because each element in the domain has a corresponding unique element in the range a union b. It's a legitimate function, but this will not correspond to any ordered pair that we are considering here. That's because C cannot be the first coordinate of any ordered pair in the Cartesian product, simply because C does not belong to this A. We are of course considering that this A and B are different from C and D. So that means if we are modeling ordered pairs using functions like this, then the Cartesian product is not the set of all functions, but some very specific functions, namely this. It is the set of those functions from 0, 1 into A union B such that f of 0, since it has to be, according to this setup, it has to be the first coordinate of our ordered pair, so it has to come from A. And f of 1 being the second coordinate, it has to come from B. And A times B is the set of all such functions. What is the benefit of this very strange way of redefining Cartesian product? It's because now you can extend this product from two sets to any number of sets. In fact, we have done so already. For example, if we have this, say, the Cartesian product of any n number of sets, then it is the set of all functions. So correspondingly, what should the type of the function be? From this into union of all the AIs such that f of I belongs to, or I should carefully see how this I corresponds with that I, because here I can take the value 0, but that's, okay. So AI plus 1 for all I lying between 0 and n minus 1. You understand that, right? So this is the definition of our Cartesian product. Now, if instead of using function you would have written your ordinary n tuple, that itself is a function of this type. So not just all n tuples, but those n tuples where the ith component belongs to AI plus 1. That is the Cartesian product. Now, using this idea, we can define the most general Cartesian product, and that is our first definition. And the definition goes like this. First item of this section, so 841, and it's been given a name as infinite Cartesian product Although we are calling it infinite, but it may not be infinite. That is, it's potentially infinite. It can become infinite. So it goes like this: let I be any set, and let and for each alpha in I, so you can pretty much understand that I here is going to act like an index set. There exists a set X alpha that you can see here also. In this case, your I is 0, 1, and the two sets are, you can call this one A1 and this, I mean A0 and this one A1. In this case, although we have the 1, 2, 3, I think this is creating a lot of confusion. 0, 1, n minus 1. In this case, this is the set I. For each such I, we have one set. Then the Cartesian product of X alpha as alpha varies over I is defined to be this set. This is defined to be equal to, just like that, the set of all functions from what to what, from I, that is the index set, into the union of all the X alphas. That is, but we have a way of saying those things, right? For example, any function from 0, 1 into A union B comes from what set? It comes from this set, right? From the power set axiom, we know that we have this notation. This is the set of all functions with this as domain and this as range. So we can apply this notation here. X alpha belongs to I, this belongs to this, such that, but not all such functions are there in the Cartesian product. Only those belong to the Cartesian product where the alpha component belongs to the alpha set. That is, X alpha belongs to X alpha for all alpha belonging to alpha. But there are some other things that also need to be made clear. And where we one of them is, of course, this notation where we recall from our power set axiom, that is the 10th one, 310 that, well, the author has written beta here. You can in fact write anything, but let's just stick to what is given in the text. X alpha belongs to X alpha for all, yeah, fine. Where we recall that this is the set of all functions with domain I and range union of all these x betas. Okay, so that is the meaning of this notation. And x alpha, as alpha varies over I, is that function in our set of functions which assigns the element x alpha in x alpha to each input alpha in I. Okay, so that is the Cartesian product. So that means in general any Cartesian product is actually a set of functions. Not all functions, but some special types of functions. That is, functions that satisfy some extra condition. Now, it does not matter what the cardinality of I is. If I has cardinality 2, then actually there will be two sets. X, that is two x's, two x betas, maybe x1 and x2, depends on what you take I as. If I has any general finite cardinality, say n, then there will be n sets, but I may be infinite also. Now that possibility is also there. So that's why we have called it infinite Cartesian product. That means it can be infinite also, not always infinite necessarily, but it can be infinite. And note that I can be actually be the set of all real numbers also. For every real number you can have a set corresponding to that real number. So the Cartesian product of all those sets can also be formed like this now. Fine, so this is just a notion, a definition, a new definition. But what about the axiom of choice? That we are now going to see. But before we do that, let us recall one lemma that we already know from before. That is lemma, I think it's 3.5.12. In that lemma, what we proved is that if we are given a finite number of non-empty sets, then their Cartesian product is also non-empty. That was the lemma. It was a result that we proved from other axioms of set theory. That is, if you have any finite number of non-empty sets, then their Cartesian product is also non-empty. The axiom of choice asserts that this happens even when you have infinitely many sets. Okay, so that's what this axiom of choice asserts extra, but a part of the axiom of choice is actually this lemma itself. Depending on whether I is finite or infinite, if I is finite, then the axiom states precisely what this lemma states. But if I is infinite, then that is something new. And I forgot to discuss about one example that comes before all these things happen. But that example is just, let me just simply show it here. It's something very trivial. That is actually the next item after this definition. So it is 842. So what this example says is just simply this. For any sets I and X, the Cartesian product of X as alpha varies over I. At first glance, it may seem like a very confusing thing. We do not see X alpha here, but what this means is that for every alpha in I, X alpha is actually equal to X. And this Cartesian product is going to be the set of all functions from I into X. The author asks why. See, we already know that the Cartesian product, any such Cartesian product, is a subset of this set. So what I'm saying here is that you go to the general thing. This Cartesian product is a subset of the set of all functions from I into the union of the sets whose Cartesian product we are considering. Why? That's because the definition itself says that this consists of all functions from here that satisfy some extra conditions. So that means this is a subset of this. You see, in this case, since each x beta is equal to x, so the union will simply be x. So we already know that this is a subset of this. But you will see that that extra condition, that the alpha component of each such function has to belong to x alpha, is automatically true for every function here, because each x alpha is actually equal to x. So that's why we have the reverse inclusion also. So in this case, we just simply get this, which is just if your I is finite, it's just another way of saying that, say all of your x's are R, and say you have 3 R's, then this is the Cartesian product of 3 copies of R that consists of all ordered triples of real numbers. And that's it, real numbers. Since all of them are real numbers, so we are going to consider all such triples. Correspondingly, we are going to consider all functions from 0, 1, 2 into the set of real numbers. That further restriction in this case just simply becomes true on those functions. So that is one thing, and there is another thing which is even more easy in this same example. So that other thing is just simply this: if the index set I is finite, Is it 0? No, it's 1. Okay. For some natural number n, then the Cartesian product that we have just now defined in that definition coincides with the Cartesian product of these sets that you previously had in that section 3.5 where we have Cartesian products, which is also almost obvious. So that is the example. And now let us going to finally see the axiom of choice formulated in terms of Cartesian products. And this axiom is going to be given number 8 because it appears in the 8th chapter. No, we cannot, it is the 12th axiom, of course, if we take into consideration that faulty axiom of universal specification is the 12th one, but actually without that axiom it's the 11th one, but we have to give it number 8.1 because it's the first axiom of this chapter, and it's just simply being called choice, the axiom of choice. Let I be a set and for each alpha in I, let x alpha, but this time we are considering non-empty sets. X alpha is a non-empty set. Then the Cartesian product of these x alphas is non-empty. That's what the axiom of choice asserts. Cartesian product is non-empty means what? That there is at least one element in this Cartesian product. What type of elements does this set have? The elements are functions that satisfy that extra condition. That is, there exists a function x alpha we know from I into the union of all the x betas such that x alpha belongs to the set x alpha for each alpha in I. Okay, so admittedly this is a little heavy in the sense that it introduces many, it's technical, right? But what is the simple idea behind this, and why is it called the axiom of choice though? What does it have to do with choice? You can interpret this whole thing very simply like this. So what is given to us? We are given some non-empty sets. How many? That depends on how large I is. If I is finite, then there are finitely many non-empty sets. If I is infinite, then there are infinitely many non-empty sets. So some non-empty sets are there, finite or infinite, we don't know and we don't care. Also note one more thing, that these sets are not necessarily disjoint. They may overlap one another, right? So what we are saying is that ultimately there exists a function x alpha from I into this set such that x alpha, the alpha output of the function, that is the output of this function when the input is alpha, is coming from x alpha. So that means this is suppose your x alpha 1, x alpha 2, x alpha 3. I do not want to label the sets like this because the sets may not be countable in number, they may be uncountable also. So from here you are choosing x alpha 1, x alpha 2, there exists an x alpha 3 and so on. So what the axiom allows us to do is to choose one element from each non-empty set. That's what it does. Why is that a big deal? Why do we need an axiom for that? That's because if you just simply say that there are infinitely many sets and I am giving you a function from I into the union of those sets in such a way that one output is coming from each set, then there is no way of proving that the function is well defined. Simply because there is no rule that is telling me which of these possibly many elements from a given set we are choosing. What is the rule of this function? That we don't know that. So the axiom makes sure or postulates that there exists at least one well-defined function that satisfies this condition. Effectively, that function allows us to choose one element from each non-empty set. That's why this function is sometimes also called a choice function, and that's where the notion of choice is coming from. So in very simple terms, it just simply means that we are given some boxes, say, and we know that each box is non-empty. Then we can pick one item from each box. That's it. That's what the axiom says. So is it not extremely plausible, and does it not feel like it should be true? Yes. But you will see, surprisingly, it will lead to many things which are highly improbable. I mean, in our general senses, intuitively, you will see that there are many things which are highly improbable that come out as consequences of the axiom of choice. That is the main reason that many mathematicians did not want to accept this axiom when it was first introduced. And one of those things is Banach-Tarski paradox, which we will see in a later chapter. Okay, so I am ending the video here itself. There are some other things in this section. Other things means there is a result that we will see, that we will use the axiom of choice to prove that result. But we will see that next week. And that's just it for tonight. Our next video is this coming Tuesday, and on Tuesday we go back to Herstein's group theory. So see you on Tuesday with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.